An isolated ground is a grounding system designed to remain separate from the service ground and other grounding systems within a building. It's often employed in scenarios demanding a high degree of electrical noise immunity, such as installations with sensitive electronic equipment or medical devices. The question of whether an isolated ground is necessary for lighting panels is a common one. Typically, isolated grounds are not a standard requirement for general lighting panels. However, there are specific exceptions where their use becomes crucial. These exceptions include, firstly, medical facilities, particularly those with critical care areas where the integrity of electrical systems is paramount. Secondly, laboratories or testing facilities where sensitive instruments are susceptible to electrical interference. And thirdly, electronic installations where a clean ground is essential for proper operation. In most standard applications, lighting panels are integrated into a grounded system through a grounding conductor, usually a green or bare wire. This conductor provides a path for fault current to return to the source, facilitating the operation of overcurrent protection devices like circuit breakers or fuses. When lighting panels are installed using rigid metal conduit, or RMC, the conduit itself can serve as the grounding conductor, providing a continuous and robust ground path. In situations where an isolated ground is indeed necessary, a separate isolated grounding conductor is installed. This conductor, also green or bare, runs independently from the standard grounding system. The key principle is that the isolated grounding conductor must not come into contact with the regular grounding system, thus preventing the introduction of noise and interference. Now let's consider the connection of this isolated grounding conductor. If the main distribution panel, or MDP, and service are also configured as isolated, the isolated grounding conductor from the lighting panels can be directly connected to the isolated ground within the MDP and service. This creates a fully isolated grounding system. Conversely, if the MDP and service are not isolated, the isolated grounding conductor from the lighting panels can still be employed. However, in this case, it's critical to maintain its separation from all other grounding systems throughout the building. This separation is what preserves the integrity of the isolated ground. To recap, in most typical installations, an isolated ground is not a prerequisite for lighting panels. Nevertheless, should the need arise, implementing an isolated ground involves installing a dedicated isolated grounding conductor. This conductor must remain entirely independent of the service ground and any other grounding systems present in the building. Now let's delve deeper into the technical aspects of grounding and isolated grounding systems. Grounding, in general, serves two primary purposes. Firstly, it provides a low impedance path for fault current, enabling overcurrent protection devices to quickly and safely clear faults. And secondly, it helps to stabilize voltage and reduce electrical noise. A properly grounded system minimizes the risk of electrical shock and equipment damage. The National Electrical Code, or NEC, provides comprehensive guidelines for grounding and bonding electrical systems. These guidelines are crucial for ensuring the safety and reliability of electrical installations. Article 250.4 of the NEC, for example, outlines the general requirements for grounding and bonding. It emphasizes the importance of creating a permanent and continuous electrical path to ground. Isolated grounding, as mentioned earlier, takes a different approach. It aims to create a ground reference that is free from noise and interference generated by other equipment and systems. This is achieved by isolating the ground conductor from the metal enclosures and raceways of the electrical system. The NEC addresses isolated grounding in section 250.96b. This section permits the use of isolated grounding conductors for sensitive electronic equipment, provided that certain conditions are met. The isolated grounding conductor must be identified by orange coloring or marking, and it must be installed in accordance with the NEC requirements. When installing an isolated ground, it's crucial to pay attention to the details. Firstly, the isolated grounding conductor should be run directly from the equipment to the designated isolated ground point in the MDP or service. Secondly, the conductor should be kept as short as possible to minimize impedance. Thirdly, all connections should be made with high-quality connectors and properly torqued to ensure a reliable electrical connection. Now let's talk about some common misconceptions regarding isolated grounds. One misconception is that an isolated ground eliminates all electrical noise. While it significantly reduces noise, it doesn't completely eliminate it. Some noise can still be coupled through capacitive or inductive effects. Another misconception is that an isolated ground is a substitute for proper grounding and bonding. It's essential to have a properly grounded and bonded electrical system, regardless of whether an isolated ground is used. The isolated ground is simply an additional measure to reduce noise in specific applications. In the context of lighting panels, the decision to use an isolated ground should be based on a careful assessment of the specific requirements of the installation. If the lighting panels are serving sensitive equipment, or if there is a history of electrical noise problems, an isolated ground may be a worthwhile investment. However, in most standard lighting applications, a properly grounded system using RMC or grounding conductor will provide adequate performance. It's also important to consider the cost of installing an isolated ground. It requires additional materials and labor, which can add to the overall project cost. Therefore, it's essential to weigh the benefits against the cost before making a decision. Another important aspect to consider is the inspection and testing of the grounding system. After installation, the grounding system should be thoroughly inspected and tested to ensure that it meets the NEC requirements and that it is functioning properly. This includes verifying the continuity of the grounding conductors and measuring the ground impedance. Regular inspections and testing should also be performed periodically to maintain the integrity of the grounding system. In conclusion, the use of an isolated ground for lighting panels is not a one-size-fits-all solution. It depends on the specific requirements of the installation and the potential for electrical noise problems. In most cases, a properly grounded system using RMC or a grounding conductor will suffice. However, in sensitive applications, an isolated ground can provide an additional level of noise reduction. Always consult with a qualified electrical engineer or electrician to determine the best grounding solution for your specific needs. Remember to adhere to all applicable codes and standards, including the NEC, to ensure the safety and reliability of your electrical installation. The NEC provides specific requirements for grounding and bonding, and it's crucial to follow these requirements to prevent electrical hazards and ensure the proper operation of equipment. The isolated grounding conductor should be green or bare, and it should be installed in accordance with the NEC requirements. The conductor should be run directly from the equipment to the designated isolated ground point in the MDP or service, and it should be kept as short as possible to minimize impedance. All connections should be made with high-quality connectors and properly torqued to ensure a reliable electrical connection. Another important aspect to consider is the coordination of the grounding system with the overcurrent protection devices. The grounding system should be designed to provide a low impedance path for fault current, enabling the overcurrent protection devices to quickly and safely clear faults. This requires careful selection and coordination of the grounding conductors, bonding jumpers, and overcurrent protection devices. Finally, it's important to remember that grounding is just one aspect of electrical safety. Other important safety measures include proper insulation, overcurrent protection, and ground fault protection. By implementing a comprehensive electrical safety program, you can minimize the risk of electrical hazards and protect people and equipment. To delve further into the specifics, let's consider some practical examples. Imagine a recording studio where sensitive audio equipment is used. In this scenario, even minute amounts of electrical noise can significantly degrade the quality of recordings. An isolated ground for the lighting panels in the studio could help minimize interference and ensure clean audio signals. Conversely, consider a typical office building with standard fluorescent lighting. In this case, the benefits of an isolated ground for the lighting panels would likely be minimal, and the added cost would not be justified. A properly grounded system using RMC or a grounding conductor would provide adequate performance. The decision ultimately hinges on a thorough evaluation of the potential for electrical noise and the sensitivity of the equipment being served. Another factor to consider is the age and condition of the existing electrical system. In older buildings, the grounding system may be inadequate or outdated, making it more susceptible to noise problems. In such cases, upgrading the grounding system, including the installation of an isolated ground if necessary, may be a worthwhile investment. It's also important to be aware of potential sources of electrical noise in the building. These sources can include things like motors, transformers, and electronic equipment. By identifying and mitigating these noise sources, you can reduce the need for an isolated ground. For instance, using line filters or surge suppressors on noisy equipment can help to reduce the amount of noise that is injected into the electrical system. Additionally, proper wiring practices, such as separating power and signal cables, can help to minimize noise coupling. When designing and installing a grounding system, it's crucial to follow the manufacturer's instructions and recommendations. Different manufacturers may have specific requirements for grounding their equipment, and it's important to adhere to these requirements to ensure proper performance and safety. It's also important to use the correct size and type of grounding conductors. The size of the grounding conductor should be based on the size of the circuit conductors, as specified in the NEC. The type of grounding conductor should be suitable for the environment in which it is installed. For example, in corrosive environments, a copper grounding conductor with a protective coating may be required. In addition to the NEC, there may be other applicable codes and standards that govern the installation of electrical systems. It's important to be aware of these codes and standards and to comply with them. For example, in some jurisdictions, there may be local amendments to the NEC that impose additional requirements for grounding. In the healthcare setting, the requirements for grounding are particularly stringent. This is because medical equipment is often used in close proximity to patients, and even small amounts of electrical leakage can pose a serious risk. The NEC has specific requirements for grounding in healthcare facilities, and it's crucial to follow these requirements to ensure patient safety. In addition to grounding, bonding is another important aspect of electrical safety. Bonding is the process of connecting all metal parts of the electrical system together to create a common ground potential. This helps to prevent voltage differences between different metal parts, which can reduce the risk of electrical shock. The NEC has specific requirements for bonding, and it's important to follow these requirements to ensure a safe electrical system. In conclusion, grounding and bonding are essential components of a safe and reliable electrical system. By following the NEC requirements and using good electrical practices, you can minimize the risk of electrical hazards and ensure the proper operation of equipment. If you have any questions or concerns about grounding or bonding, consult with a qualified electrical engineer or electrician. The proper implementation of electrical grounding and bonding involves a comprehensive understanding of electrical principles, codes, and standards. It's not merely a matter of connecting wires, it's about creating a safe and effective electrical system that protects people and property. A well-designed and installed grounding system will provide a low impedance path for fault current, enabling overcurrent protection devices to quickly and safely clear faults. This helps to prevent electrical fires and other hazards. A properly grounded system also helps to stabilize voltage and reduce electrical noise, which can improve the performance of sensitive equipment.